Hello students, in the previous lecture we had proved Rolle's theorem and will and also come to know about its theoretical interpretation. So let me define what is Rolle's theorem. Let fx be any function which is defined in a closed interval AB subset of the domain of that function. And first condition is fx is continuous in that closed interval AB, and fx is differentiable in that open interval B, and f of a is equal to f of b, and f of a equal to b is equal to f of a equal to f of b is equal to 0, f equal to f b. Then there is a point C belonging to open interval such that the tangent is parallel to x-axis. Now we will apply this term to we'll search the function which will satisfy Rolle's theorem or which will not satisfy the Rolle's theorem. So we'll see the function, how to apply Rolle's theorem on the function. So let's discuss for first problem. Verify Rolle's theorem for the function fx is equal to x square minus 5x plus 4 in the closed interval 1 to 4. So given it, fx is equal to x square minus 5x plus 4. This is a quadratic polynomial, means it is a polynomial function. The domain of this function will be all real numbers. We want to discuss in the closed interval minus 1 to 4. So if this function is defined for all values of x, therefore this function will be defined in the closed interval 1 to 4 with subset of set of real numbers. So since f is polynomial, right? So it's well defined in this closed interval. Since every polynomial in x is continuous for all real numbers, therefore continuous in this closed interval because this is subset of real numbers. Therefore this is continuous in this closed interval. If we differentiate fx, we got 2x minus 5, which is a polynomial, which is also polynomial and exists for all values of x. Therefore, if this derivative, after differential function for fx, we got new function. It is defined in for real numbers. Therefore, it is defined in the open interval 1 to 4. Defined all real numbers. Therefore, defined in, and this implies fx exists for all x belonging to the how to see that method. Now second is f of a 1 is 0, f of b is equal to 0, f of b is equal to fb. F of b is equal to 0. Therefore, f satisfies all the three conditions of Rolle's theorem, implies there is a point C belonging to the open interval 1 to 4 such that f is equal to 0. So put in the derivative of fx, replace x by c and put that equal to 0. Solve this equation for c, then check whether this point belongs to the open interval. If this point belongs to the open interval, means Rolle's theorem is satisfied at this point in this interval. If this point does not belong to the open interval, well, we have to search a point C which belongs to this open interval such that first derivative at that point is equal to 0. Means Rolle's theorem is satisfied in that closure. Right? Now the next problem is verify Rolle's theorem for the following function. Function is this is a trigonometric function fx is equal to cos of 2 into x minus pi by 4 in the interval closed interval 0 to pi by 2. Now this function, let's simplify this function. Cos of multiplied by 2, cos of 2x minus pi by 2 is pi by 4 become pi by 2, and in the interval 0 to going to 0. Now take a minus common. Cos minus cos theta is going to become cos pi by 2 minus 2x. Now cos of minus pi by 2 minus x, this is like fourth quadrant. Cos of pi by 2 minus theta is equal to sin theta equal to sin of 2x in the interval. Now our we separate the function, and the simplest form is the trigonometric function sin function in the interval 0 to pi. Now we know that the domain of this function sin 2x is all real numbers. So this is well defined for all real numbers. Therefore, well defined this in closed interval 0 to pi. Now, since the curve is a continuous function for all x, it's continuous for all x, because we don't have any point where with the value which just does not exist. Continuous for all x implies this is continuous in this closed interval. We have differentiated fx at s is equal to 2 cos 2x, which exists in this interval 0 by 2. Therefore, f is differentiable in this interval. Differentiated. Now, this new function which exists in this interval of interval, therefore, f is differentiable. Now, sine of f of 0 is equal to sine 0 is equal to f of pi by 2 is equal to f pi by 2. So, f of 0 is equal to f of pi. F satisfies which is equal to again equal to 0. F satisfies both the conditions Rolle all the conditions Rolle therefore that's point C belongs to the interval 0 by 2 such that f less equal to 0. Now again we find the C which line belongs to this interval at which f less is equal to 0. For this to 0, put the value of C in the first derivative of fx and find the 2 cos 2 is equal to 0 divided by 2 for this to 0 cos 2 is equal to 0 cos 2 so 0 when 2 is equal to pi by 2 or multiple of pi by 2, 3 pi by 2, 5 by 2, minus pi by 2, minus 6 by 2 and so on. Now remains to find the point C which belongs to this interval. Now therefore if you see this C will be equal to pi by 4 and 3 by 4 and so on. Only this pi by 4 is the value which belongs to this for which f is equal to 0. So implies there this point C belonging to pi by 4 belongs to this such that Rolle's theorem is satisfied. So for function, for given function, f is equal to cos of 2 into x minus 5. Now the next problem is verify Rolle's theorem for the function fx is equal to under root of 1 minus x square for x belong to the this closed root of minus 1 to 1. Now let me know what is the domain of this function. So domains this function are those values of x for which the term under the root is greater than equal to 0. So that is this is greater than 0. Adding minus both sides, you got this implies x is greater than equal to minus 1 is greater than equal to x square. This implies reversing this x square is less than equal to 1. The positive square both sides is equal to modulus x is less than 1 implies minus 1 is less than x is less than 1. So means x belongs to minus 1 to 1. So this function is well defined in this interval. Well defined this interval closed interval. Therefore, fx is continuous in this interval. Continuous interval. Continuous interval implies continuous interval. First one is to hold true. We differentiated fx. This is half of 1 minus x square equal minus half into 2x. This become after simplification become x upon root of 1 minus x square, which exists in the interval minus 1. But because it is undefined, when x 1, it will become undefined at 1 and minus 1. So we have excluded the point. Differential function. We got a function after differential fx. So new function which is exist in the open to this, it will become undefined at 1 and minus 1. So we exclude the point this from this interval. So if this function exists in this interval, implies f is differentiable. Right? And f1 is equal to f minus 1 is equal to equal and equal to 0. This implies fx satisfies all the three conditions theorem, implies this point C belongs to the interval minus 1 to 1 such that f is equal to 0. Put the value in place of fx, see x equal to C, and so simplify this equation and find search for the point C belonging to this interval. So for this to be 0, C upon this equal to 0. C multiply cross multiplying C for this to be 0, C must be equal to 0. C is equal to 0 belongs to the interval minus 1 to 1 implies there is a point C belongs to open intervals so that the Rolle's theorem is satisfied. Discuss the applicability of Rolle's theorem to the function modulus of x. That is modulus x in the interval. So now let me know the definition of modulus x. Fx is equal to modulus x. Modulus x is equal to minus x if x is less than 0. Equal to 0 if x is equal to 1. 0 is equal to x if x is greater. So what this function is? Fx is continuous for all number. Therefore, f is continuous in this polynomial, constant, polynomial. That is continuous for all the numbers. For the number, the continuous is. Now we know it. We have proved it in the previous chapter that modulus x is not differentiable at 0. That is, If you differentiate, if you find the left derivative at 0, it comes out to -1, and you can prove it here also. If you find the right derivative at 0, it comes out to 1. So left derivative is not equal to right derivative, means fx equal modulus x is not differentiable at 0. So we have a point 0 belongs to the open interval, 0 belongs to open interval minus 1 to 1, such that the function is not differentiable. So we got a contradictory point. If it is differentiable at all points between -1, there are infinite points. If you find a point at which this is not differentiable, then the then the differentiability, condition of differentiability violates in this interval. If we have a point belonging to this interval at which derivative function not differentiable, means the condition of differentiability function in the open interval violates. So this violation, this implies we are not supposed to see the next third condition, implies the Rolle's theorem is not applicable to this function, the function fx equal modulus x in the interval closing to -1. The next problem is, let fx, gx and hx be three continuous functions in the closed interval AB and differentiate the open interval AB. Show that the exists point C belonging to the open interval AB such that f dash c, g dash c, G dash C, H dash C, F A, G A, H A, F B, G B, H B, modulus this equal to 0. Now, from the first row, we have to guess what this phi x will be, which will satisfy the Rolle's theorem. Phi x will be, the differential this function means if it is a variable, then phi c will become phi c c. So we will assume that this will be fx, gx, and hx, and other two will be the same. We suppose this will be phi x. Now they are constants. FA, GA, HA, FB, GB, HB, they are real numbers. So when we operate this determinant with by using the property of determinants, we obtain phi x, an expression in terms of fx, gx, and hx, which were and ABC are constant. So we know that fx, gx given, fx, gx, hx are continuous in the closed interval AB. Therefore, algebraic sum phi x is algebraic sum of these two continuous functions. Therefore, phi x is continuous in the closed. Now fx, gx is hx are the differential open interval. Therefore, phi x is differential open interval. Therefore, phi x is differential open interval. B. Phi a is equal to phi b. Phi a is equal to phi b. Phi a is equal to phi b. This row, if you will x by a, this row become identical. Determinant is equal to 0. Phi b. If you will x by b, phi b is equal to first and third row become identical. Determinant is equal to 0. So phi equal to phi b is equal to 0. Implies there's a point phi x satisfies all the three conditions theorem, implies this point c belongs to b, phi x equal to 0, phi x equal to right. That's all. Thank you very much.